Then I stopped. Then the push forward of m nabla by the Frobenius satisfy the following. The rank is exactly equal to p times the rank, or the dimension is the same, rank of m. And there is another point. If we have then this example, we saw it before. It's just we extend the scalar. For that, we don't need a finite extension. In that case, we should choose this one. And but I already denoted by this before. Then the pullback. We set. And the pullback of n nabla. This is just the scalar extension with respect to this sphere. And in that case, the interesting point is to see after what is the relationship between the radius of convergence between the two. And because of that, we can do better. It's exactly the same. In that case, nothing changed. Then I give some properties. No, before that. Then omega I, nabla I, to be just a differential module on P with dp minus I, and this I is in the set 0 p minus 1. This just means it's if we want to know to have the same derivative, it's a kind of this module. E over p. The point is that in this fields, this differential equation don't have any solution. But however, if we extend the scalar, then we will obtain the solution. That's why that's the point that they will make some problems about the link between the differential module and such stuff. Then we have the following property. And we consider proposition. Let then the push forward of M is isomorphic. Yeah, it's isomorphic. Okay, and 0 minus 1. Then this is the first one. This is the second one, is that if I have something like that, prime, then it is the direct sum just I pull back, after that I push forward, but if I push forward, it will be many of them. It's just the translate of many of this copy. And in the other sense, we pull back, after that we push forward, we obtain isomorphic. Just I take the sum p times of M. And the result that we will need later to compute our is H of M is isomorphic. This means even for the solution, and this means if M don't admit solution, then it's a push forward don't admit solution. If it is the app is surjective, it remains surjective, which is obvious because the map that doesn't change. It's just a restriction of the scalar. But we will see that just if we put it and use it later, it is useful. And the last point is the following. Then, if we consider the push forward of two differential model over here, just I add M1 nabla 1, M2 nabla 2. It's as a differential model over the same thing. And it's also, if I just combine them, then I will obtain such thing. Then the most important proposition is the following. The point is that can we, for example, have for any differential here, differential modules over these fields, can we find a differential module here that if we take the pullback of this differential module, we get this differential module? In some condition, this is possible, and this is the following theorem by Crystal and Dwork. And the point is that the spectral radii need to not be exactly equal to omega, the radii of the point. And it's called this element, it's called the Frobenius antecedent. And if the smallest spectral radii is greater than omega, rho, here the radius of the point is exactly equal to rho, then there exists a unique optoisomorphism, sure. Differential module. Such that the pullback of is isomorphic to M nabla. And in that case, we have the spectral radius of M prime. The smallest one is equal to 1 of M power P. And this means in particular, if it is greater than this value, it can be less than this value. After this one, no, sorry, it's not what I want to put here. It's the spectral. It's the spectral property. In particular, by saying that maybe we can find the point with that is that if we use the cyclic basis, and in that case, even if we have, for example, small the absolute value of some roots will be small, then this doesn't matter. Then we can even use them as, in some sense, we can say that if we suppose that my differential module is pure, and we consider then this just means that the spectral norm will be exactly equal to the absolute value of this root, even if its absolute value is less than d. But be careful, but unfortunately we cannot use it for any. If this one, for example, is equal, we don't have that. However, we can prove the following theorem, but just give the it will give us a link between the radii of convergence of my initial module and the push forward, and by that I can do the decomposition. Then we consider, but in order to prove that, we need this result. I cannot prove it because we don't have time. I just will prove the last theorem that we did. We will got the decomposition. Multiset, just I will contain them with multiplicity, not lose anyone. Then they are this set. Then just for example, here, the radii of this point is rho power p. And here, this is p minus 1 time. And here it's p times. Then by using this, these two results, we can prove the following theorem or proposition easily. It's not complicated. Just it's a fact of this two one. Then I will not. Then the point, if we have before for the first decomposition, when we decompose, we need that the radius be small. Now we can, using this two result, we can by using if the previous one, by using the decomposition with small radius, but when we use the push forward, we can come back to the case of small radius, and that's why we use the same result, and this will lead to a decomposition of two differential modules. Then let then here we will assume that they are smaller, they are different. And just since the two differential modules are irreducible, this means that they are pure. And this, oh, sorry, here it's just one. And this means that all the radii are equal to this. This means they don't have the same radii, that way we can say. And in that case, and this is exactly equivalent to say that if we have an exact sequence here, then probably we will have V is isomorphic to the direct sum. Cannot be something else. And this is the result that we will use. The idea is if the two one are small, then we can do the previous result. If there is one that is equal, if the smallest one is equal to omega O, for example, then for one we will use the for one we will use this one, and for the other one we will use the push forward, and we can prove in that case that the H1 of this tensor product is exactly equal to zero, because they have small radii and they are different. And that's why by taking the push forward of the two, by using those property, then we will obtain this property. Then we need this property, and here, and we will obtain something nice here, that it is a direct sum of here's an element that the push word, and here we will get it's called the thing that this one is called this differential module is called the Frobenius antecedent, and in here we've got the Frobenius antecedent, and you can take it this over, and since what is inside has h1 equal to h1 equal to 0, then so is for m, and since it is this one, if this one is if this one is 0, then this one is 0 because it's a direct sum, and after that we can use this one from this equality to get it equal to 0. And otherwise, if both are strictly less, then we can use the Frobenius antecedent and go back to this case. I will not write it. I will not write. I just give the idea. Now I can give the term of the strong decomposition. Then let and that's why we can decompose using the same idea as we already did before. Just it doesn't matter of the choice of the derivative, because if by multiplying, for example, by this one, I will get a differential module. Then if I can decompose this one, I can decompose the other one. This is not depending on the choice of the derivative. Unique decomposition, you can say. Unique. By the existence, we can prove the uniqueness. Such that here it's depend on the radius of convergence. The radius of convergence is something between rho and strictly greater than. Oh, I can write it. Before it was with respect to the spectral node, but here I specified that it is with respect to the but it's can see it as the same, or every. Then the proof. Then if my differential module is irreducible, then we cannot say anything. We cannot decompose it more, and for sure we will have all the radii are equal. Now, if we assume that my differential module is not irreducible, then it means then we will proceed by induction. Then here just if from 0 every non-zero otherwise it doesn't have any sense. Yes, I really cool. There exists a short exact sequence. For example, you just need, if you consider the Jordan-Holder sequence, by considering the Jordan-Holder sequence, then just this one is the first term, and we take the quotient of then by the induction hypothesis, we have M1 is equal to something like S0 M1S. And in that case, with all the other part, then we just need, if we set R, for example, equal are equal to the spectral, then we have something like that. Then we will probably have, we know that then with each term, it's a direct sum with M2. However, the only problem is that this one, then we consider that probably we got something like that, that I will set to be MR. Then in that case, we know, because they have the same spectral radii, that this just implies that there exists something like that. And in that case, we will got that M is MR is something like that, plus probably something by using the previous theorem. And then we got our decomposition. Then we can stop here and the course finish here. If you have any question. Then today was the last course, then good luck.